Dear students, welcome to another day's lecture in Elements of Machine Design. Today, we will start where we have left yesterday. We were discussing about the bearings. Now, let us see about the selection of bearings from the manufacturer's catalog. You see, every manufacturer, for example, if there is a SKF company, SKF bearings, they have manufacturer's catalog. From that, how to select an appropriate bearing for our application. That's what we are going to see. You see, this is often asked in your exams. So they may ask you to write the step-by-step designing procedure, step-by-step procedure in choosing a journal bearing, in selecting a journal bearing, in selecting a bearing for that matter. Okay. So let us see. The following steps must be adopted in selecting the bearing from the manufacturer's catalog. The first thing is you have to see what is the radial load. Radial load means that load that is coming perpendicular to the axis of the shaft. Radial load, the axis load, axial load. Axial load means that which is coming from the side like side thrust. What is that? So radial load is FR, axial load is FA. These two you have to find out what are those things that are coming. Okay, and then now decide the diameter of the shaft on which the bearing is mounted. You see, the shaft diameter depending upon how much torque and how much bending moment are coming upon that, and how much axial thrust is coming. Though we have not seen axial thrust problems in the designing shaft, okay, but in real life applications you have to consider what are the axial loads coming also, and then depending upon that you have to find out the diameter of the shaft. This is the second step. Then for the selection of proper size of the bearing suitable for given application. What is the application? Specified with the speed. What is the speed? And what is the available space? You see, on the basis of their application, the speed of the operation, and the space available, you have to choose the bearing. Select the bearing. From where will you select? From the catalog you will select. Then, fourth one, select the basic static rating CO of the selected bearing from the catalog. So once you have selected on that catalog, you will get CO. Then calculate VA upon VFR, FA upon VFR and FA upon CO. Okay, these ratios you have to calculate. Find the value of X and Y, that is radial thrust factor from the catalog. These values depend on FA upon FR and FA upon CO. These values of X and Y you have to find out from that catalog on the basis of these two ratios. Okay. Then find the value of load factor Ka from the catalog. You see, for a given bearing, all these things will be there in the catalog. Then calculate the dynamic load using this relation. Dynamic load PE equivalent to dynamic load. E stands for equivalent. Meaning is equal to X into V into VFA plus YFA whole bracket Ka. Then calculate the approximate life of the bearing in hours from the type of bearing, operation and type of machinery, that is it depends upon the application. You have to calculate the life. Then calculate the required basic dynamic capacity for the bearing using this L10 relation. L10 is C upon PE raised to the power A. The required basic dynamic capacity This is that C can be calculated from this. Once you know the C, okay, this is the required thing, and what is given in the catalog, you see. Okay, so if the basic dynamic capacity of the bearing is more than the required one, then you can stop there. So you, what selection you have made is the right selection. Okay, otherwise you have to go and recalculate. You have to um, repeat the procedure again. Okay, the same thing can be shown in the form of a flow chart. Here, this flow chart shows the selection procedure of the bearing from the manufacturer's catalog. Here you start, then you have to input. Uh, First, you have to find out what is FR, FA, shaft diameter, and what application. All these things you should be having. Then you are selecting from the caterers uh, from the catalog the type of the bearing. Then select bearing of extra light series. Okay, here itself you are selecting bearing. Then you have to find out CO, C. Okay, this FA upon FR ratio or FA upon CO ratio. Then you have to select what is choose X and Y. Then you have to KA and L10. These things you have to select. Then you have to calculate this equivalent load PE with this formula, and then next you have to make it put a decision box. In the decision box, is it ball bearing? Yes, no. If it is yes, A is 10 upon 3. If it is no, it is A 10 upon 3. If it is yes, A is 3. Okay, and then calculate the required dynamic loading capacity. Dynamic loading capacity is the from the L10 formula. C is equal to PE into L to the power 10 of O to the power 1 upon A. And then here the comparison is being made. Okay. And then, see, suppose the rating, the rating dynamic load capacity of the bearing is more than the required one, then we have chosen the right one, so you can stop. If it is less, then what you have to do is you have to select next series, and then you have to go back. Oh, this arrow should not be downward, it should be up. You have to go back and do all the calculations from this table onwards. Okay, from this table onwards, from here, from this box onwards. Okay, this is how you have to choose. Depending upon what is asked, you can answer. Dear students, let us see about some of the some terminologies of a Sparger. This is Sparger partially shown. Here is the axis of the shaft. Here is the hub. Here the teeth are there. Okay. So here this circle is called a root circle. Then this circle is base circle. This pitch circle and the top circle, no, that going through the top of the thing is called as outside circle or called addendum circle. This is addendum circle. Then this is the dedundum circle. Okay, this one is the dedundum circle. Outside one is addendum circle, and this is the pitch circle. Okay, like that. And this one is called as topland. Okay, and this is called a face. There's all these top portions, and the bottom portions are called as flanks. This is the flank, this is the face, and this is the face width. Okay, and on this pitch circle, from this point of the tooth to this point of the tooth is called as circular thickness. And from one point on the pitch circle to the same point on the next tooth on the pitch circle is called as circular pitch. Okay, so this is the addendum A, this is the dedendum. From pitch circle to the top is addendum, from pitch circle to the bottom is the dedendum. So this circle is addendum circle and this circle is the dedendum circle. So this is about some of the terminology of the gears. Now, in case of Sparger's Lewis equation, this is another last topic that is remaining in our syllabus, Lewis equation. This Lewis equation for static beam strength of Sparger teeth. In the accurate stress analysis of a gear tooth, that means when gears are meshing with each other, so one tooth is one gear is rotating the other gear. That means when they are meshing, one tooth is pushing the another tooth. Okay, so there are forces being transmitted. Because of the forces, stresses come upon in the gear teeth. Okay, so the accurate stress analysis of gear tooth for a particular application is very complex. It is not so easy, because there are many problems, many factors involved. What is that? There is continuous change in the application of load, because the profile is not a straight line or something, or not a circle or something. The profile is changing because there is a continuous change in the point of application of the load on the tooth profile. Okay, on the tooth, where the force is applying, it keeps on changing. And then the magnitude and the direction of the applied load also changes. That is another thing. The load also is changing, the magnitude is changing, the direction also is changing. Then the static and dynamic load due to inaccuracy of the both tooth profile. You see, in the tooth profile, you see, sometimes it should be cycloidal tooth profile, or involute tooth profile, or any other tooth profile if it is there. In that, if there are any inaccuracies or errors in machining, or when you are manufacturing, some errors have cropped in, or errors in mounting, or tooth deflection, then acceleration and stress concentration, all these factors act on the tooth, which are difficult to model mathematically. See, all these things are involved, because of which it is difficult. But in the year 1892, Wilfred Lewis, he published a research paper titled The Investigation of the Strength of Gear Tooth. So he has derived an equation for determining approximately the stress in a gear tooth, considering it to be a cantilever of the beam of uniform strength. You see here, you see in this figure, so this is one tooth he has taken of the gear. Okay, and in one tooth, you see here, you see, consider each tooth as a cantilever beam loaded by a normal load Wn. This Wn is the normal load which is coming upon that tooth. If you treat it as a cantilever, we are going to see, wow, the equation, Lewis equation. It is resolved in two components, that is tangential component Wt and radial component R. See, if the tooth profile, this one, if I draw here like this, if the tooth is there, let's say this is the tangent to the base circle. So tangent, and in this tangent Wn will be working. Okay, this is the thing, this Wn. Okay, this Wn can be resolved into two components. One is radial component, which is going perpendicular to the axis, or along the radius of the gear, and this is going tangentially. Okay, Wt. Okay, these two components, this Wn can be resolved. Okay, then now here we see what all the other things are there. This is the tooth profile. You see, this is the tooth profile. This is the width of the gear B. This is the thickness of the gear tooth T. Okay, and this is the height of the height H. Okay, these are the things which we'll be using. Okay, now come see, now those two components Wt and Wr, the tangential component Wt induces a bending stress, and if this, see, see, one is going radially, the other is going tangentially. This tangential load that is responsible for the bending, and what is the resultant? It tries to break the tooth. The radial component induces a compressive stress, and this is relatively small magnitude. Therefore, the effect of this component, radial component, can be neglected on the tooth. So WR we are not going to consider, only WT, because this is very little, the tooth can easily bear. So only WT let us consider. So the maximum bending stress may be obtained by drawing a parabola through A and tangential to the tooth curve BC. You see here, now this is A, this is B, this is C. Okay, now from here a parabola is drawn like this, that is BC as the base and passing through A parabola is drawn. Okay, this parabola by this dotted line is the shape of the parabola, has same stress at all sections. But the tooth is larger than the parabola at every section except BC. You see here, if you say A, the tooth is larger. Here also is larger. Here also, only at BC, the tooth profile, the tooth thickness and the parabola are of same size. Okay. Okay, but the tooth is larger than the parabola at every section except BC. Hence, we conclude that the maximum stress induced is so the maximum stress is coming at BC. Okay, and then the maximum value of the bending stress. You see, normally for any cantilever, we know that for a cantilever, the bending moment will be zero at the application of load, and towards the support when you go, it increases. That's what is happening here, and that sigma B at the section BC, that is the maximum bending stress, is we can give by this bending equation. You know the bending equation, sigma B by Y is M upon I. Okay, otherwise you can write it like this: sigma B is equal to M into Y upon I. Okay, now what is M? M is the bending moment. Okay, where at the support or at the section BC, you can say. Y is the distance of the neutral axis from the extreme fiber. See, if the total is T, Y will be half of this, T by 2, you can say. That is T by 2. And I is the moment of inertia. And that section there, it will be a rectangular section. For rectangular section, I is given here. You see, BT cube upon 12. BT cube upon 12. Now, to which cube should be there? To B or T? You see, this WT is in whichever direction. To that, this to whichever, see, it is parallel to T. It is not parallel to B. Okay. So, because it is parallel to T, so therefore to T it will be applied that cube. Okay, so BT cube upon 12. Earlier I said it should be to the larger of the things, but the thing is, larger of the things, no, if it is given, then the bending stress induced will be minimum. But anyway, in case of gear tooth, we are seeing that load is parallel to the thickness T. Therefore, cube should be applied to T and not B. So I is BT cube upon 12. Okay, and then what else? Okay. All these things, let us substitute in sigma B. Sigma B equation is there. M is equal to bending moment is the tangential load into the length of the cantilever. In this case, length of the cantilever is h. Okay. Then y is nothing but t by 2, and I is equal to bt cube by 12. I am seeing bt square here. It should be bt cube by 12, is it not? Yeah, it is bt cube by 12. Here by mistake they have put square. It should be cube 3. Okay, now let us simplify. W into h, you keep it as it is. This 12 and this 2 will result in 6, because you have to reverse this 12, because it is at the denominator of the denominator, so it goes up. Okay, this is 6, and this 1t cancels, so t square will remain, so bt square. Okay, and then so from this equation, what you can do is you can bring out w. This w is a tangential load. Okay, w, and this sigma b into this b into t square upon 6h. W has gone that side. Okay, this is what we have got. Okay, in this expression, see, sigma b, it is a constant value for a particular material of the gear. Okay, and in this expression, t and h are variables depending upon the size of the tooth and its tooth profile. Now, let us say, let t be t also we can write in terms of circular pitch, some constant x into circular pitch, and h also we can write as some constant k into circular pitch. Okay, so let us substitute to those two values here. So instead of t square, we will put x into pc whole square, or x square into pc square upon h is k into pc, so 6h, it becomes 6k pc. So now what we do is, this factor, which one, say this 1 pc gets cancelled, only 1 pc will be remaining. This x square upon 6k, this x square upon 6k, you term it as y, and this is known as the Lewis load form factor or tooth form factor. Okay, so wt will become sigma b into b into PC into Y. And this is the equation of the Lewis form factor. Okay, this one. Okay, and this can be written another way. Instead of PC, is replaced it with pi into M. Okay. Uh, See, this M is the module, I think. See, the quantity Y, this one, which is given by x square upon 6k, is the Lewis form factor or tooth factor, and W2 is called as the beam strength of the tooth. And this sigma B into Y, this is called strength factor or something. Today I'm asking you a quiz question. What is the which product is called a strength factor? This sigma B into Y. Okay. So now y is x square upon 6k, and then here um, x is equal to t upon pc. Okay, and h is equal to k is equal to pc into h. Okay, maybe here it should be into. Okay, this is x square, this is 6k. Here not, it is not equal to, it should be dot or into, and so this becomes a 6 square upon 6 hpc. So the value of t hpc can be determined analytically or measured from drawing. The value of y in terms of number of tooth may be, see, there will be number of different types of teeth. Okay, for 14 and a half degree composite and full depth involute system, this y should be taken. For 20 degree full depth involutes gears, we should take this, and 20 degree subsystem, we have to take this. Okay, you see this equation which is the Lewis equation, which on this one, W2 is sigma b into b into pc into y. This is the Lewis equation that is necessary to to estimate uh, the bending stress as a cantilever. Okay, so this way of finding out the bending stress, and then and estimating the bending stress involved, and then whether the tooth can withstand or not. Okay, this way is we can say this is we are designing the Sparger using Lewis equation. Okay, you see, when we are designing, sometimes one quiz question is asked, to which of the gears it is, no, now two gears are there, one meshing. The bigger one is called as gear, the smaller one is called as the pinion. So this equation, Lewis equation, is applicable to the bigger one, the gear or the pinion. Okay, this is it can be applicable to any of the two, either gear or pinion, whichever is we can say weak. Okay, on the basis of that you can design. Okay, like that, I don't know if some of the questions asked in the quiz, if you we have not touched those things and you are unable to answer, you just try to find out in the internet and try to answer. See, with this we come to the end of this unit number 6 we are finishing. So with this we have covered all the syllabus of this subject, which is the elements of machine design. Okay, So now, as part of this subject, the theory part we have considered. Now we will write the journals, practical journal. Okay. So then the practical means, actually in this subject there is nothing like going to the laboratory and doing. Okay. So I will, as time permits, I will be posting different experiments which you have to write on journal papers. You try to get journal papers. Journal papers means, those papers which are having lines on one side and blank on the other side. In that you write. Okay. And you try to understand the things. And so now for some days, uh, at least for 2 3 days, I will not post anything. And in the classroom. And if some of you have not have missed some of the lectures, okay, so what I'll do is, uh, every day every day from the beginning. Now totally we have covered around 50 lectures. Okay, in the 50 lectures our syllabus is finished. So from the beginning, what I can do is, I can open up one quiz, and I will repost one that video and that quiz every day. Okay. And whoever have missed, you can do it, you can solve it again. Even if those people who want to practice again, uh, you can do it. Okay. Only that those people who have not attempted before, okay, I will give them attendance also. Okay, this is a second chance. But what I feel, no, the quizzes should not be open for more than 2 days. So once I open the quiz, I will keep it open for 2 days and then I will close it. So like that, every day. So we don't know how many more days will have. But in the meanwhile, I'll be sending you some practical assignments for the practicals also, which you should write in the journals. And if any problems are there given, you should be able to find out the answers and give it. Okay. So with this, we thank you. We end this today's lecture, as well as our um, entire lecture series in this subject of elements of machine design. Thank you very much.